Okay, so we're finished with Chapter 7 last time. We're going to go on to Chapter 4, and we're going to finish Chapter 4 today, 45-minute chapter. This is reasonable because it's two of the three sections are extremely similar to single variable analogs. And you're just going to notice, oh my gosh, it's exactly the same thing. There's just more variables running around, and it changes a couple things. Then section 4.3 is where things will get interesting, and there's a couple things to talk about, but most of what we're going to talk about in 4.3 is going to be the particulars of how some challenging algebra works out at the end. So anyway, here we go. Section 4.1, we're going to talk about Taylor's theorem, and y'all recall the Taylor polynomial, I'm sure, from single variable calculus, right? So there's the formula, but then let's also ask the question, why do we care about that formula? Where does it come from? And there's different points of view on this, right? What I think is the easiest to digest point of view is this right here. This is among all polynomials, this is the one among polynomials of degree k that best approximates the function. And what do I mean by that? Well, it is a perfect mimic of f in terms of values and derivatives up to order k. Right? So this is, doing the best it possibly can to be exactly what f is at the point A, at least in terms of values and derivatives. Okay. All right. So that's a pretty reasonable way to approach wanting to approximate a function. So I tell you what, why don't we do that exact same thing in the multivariable setting? And we're just going to ask, okay, given a multivariable function, real valued multivariable function, how would we mimic that function in terms of values and derivatives? Well, the function has a value, and it has several partial derivatives. It has several more second partials, et cetera, and it has a whole bunch of kth order partials. And let's just say, let's look for a polynomial of degree k. We're looking for the best possible polynomial in terms of mimicking f at the point A. Same idea. Right? And it turns out there is exactly one polynomial that agrees with f in value and all those partials, and here it is. So this is our multivariable degree 2, by the way. I'm only going to show you the formula for degree 2. Things get a little weirder beyond that. We don't have any need for it in this course. So degree 2 Taylor polynomial for a multivariable function. And you're going to notice a couple things right off the bat. First of all, the first two terms are the linear approximation. It's exactly the linear approximation. So just like with a regular Taylor polynomial, you can think of this as sort of an extension of a linear approximation. You're going to notice as well, if you look at the second order term, there is a 1/2, just like in single variable. There's two different factors of x minus a, which of course are now vectors, just like in single variable. And there is something related to second derivatives, just like in single variable, but now we're going to see that there are some pretty significant differences here. For one thing, this is a matrix. It's called the Hessian matrix, the matrix of all the second partials. You'll notice that not only are these vectors, but we're not multiplying them. One of them gets multiplied by the matrix first, and then we are dot producting those the two resulting vectors. So it's different, but nevertheless, it's kind of analogous. Or here's another way to say it, what I think is arguably a better way to say it. You should think of this as being the natural formula. And the single variable version that we've seen previously, think of that as being a special case of this more general formula. And of course, when there is only one variable, this simplifies exactly to the single variable case. How are we doing? Is everybody with me so far? Okay. Well, Y'all know how to compute second partials. Y'all know how to multiply matrices times vectors. Y'all know how to do dot products. And so y'all know how to write down these second order Taylor polynomials. And we are done with section 4.1. That's quick. Now, there's other stuff to read in there. Make sure to read through that. But I don't think it requires discussion. I think y'all can read that stuff. Okay, on to 4.2. So I'm going to give you all a take on single variable optimization. This may be different from previous takes you may have seen. I like to do things this way because it sets up an analogy. Y'all recall I like to do this a lot. If you take a certain point of view on the single variable version, the multivariable version is kind of the same thing by extension. Okay, so here's the take I want to give you. If you are looking at some sort of a domain and you're trying to maximize or minimize either one, some function, and here's the graph of some function. It's made up, right? Let's not get into formulas and stuff. Given that setup, I claim that most of the points in the domain I can eliminate based on these conditions. These three conditions. So how does this argument work? Well, let's see. How would I go about eliminating, for example, this point right there? How would I eliminate that? Well, first of all, it's in the interior, which means from this point I can go either forward or backward. I can go either direction. I'm not near the edge. I got all the flexibility I might need. Is that me or somebody else? Okay. Okay. I just wanted to make sure it wasn't me. No problem. Okay, so it's in the interior. The function is differentiable. Why do we need that? Well, because we need the derivative to mean something, and we're about to use the derivative. Lastly, and I'm just going to, hand wave to the picture. It would appear, and this is something y'all know how to do the algebra for, it would appear that f prime is not 0. And I claim these three conditions alone allow me to argue as follows. Well, this point, look, one way or the other, the function is increasing. Now, in this case, it's as I go to the left, the function would be increasing. Now, let's think this through for a second. If the function is still in the process of increasing, that couldn't possibly be a maximum. Does that make sense? If it's still getting bigger, right? So, definitely still increasing, therefore definitely not the maximizer we're looking for. And good news, these conditions allow me to eliminate practically every point in the domain. Right? Most of these points are definitely not maximizers by exactly this argument. Now, which points do we fail to eliminate? And let's just take a quick moment to recognize, I use that term deliberately, fail, right? We have failed to eliminate, for example, this point right here. That doesn't mean that we get to draw some conclusion about this point. It means that we don't know what's going on there because our argument doesn't apply and we just don't know anything, right? So, which are the points in question? Well, it's points where one or the other of these conditions fails, right? If any one of these three conditions fails, we can't make the argument we need to make. Is everybody good with that? Yeah? If the assumptions of your argument don't work, then the argument doesn't work. Okay, so this is what it would look like. If one or the other of these arguments fail, we're either looking at a boundary point, or we're looking at a point where the function fails to be differentiable, or we're looking at a point where the derivative is exactly 0. And so these are what we're going to call critical points, which is, I like to call it a euphemism. Critical point is a euphemism for we don't know what to do about it. We don't know what's going on at those points, right? And I'm externalizing, and I don't want to admit that I don't know what's going on. I'm going to label them. It's a them problem, that they are critical points. It's total cop-out. Does that make sense? Okay. All right. Okay, so we're going to do the exact same thing in the multivariable setting. And here's the argument. It's totally analogous to what we just talked about. I claim these three conditions allow us to eliminate most of the points in the domain. Just to get everything set up, let's suppose we're looking at this domain. And we're looking at the graph again, just for visual convenience. And so we've got this graph. And among all these points in the domain, I want to find where is the function. And I'm just going to say maximized. We could be on the lookout for an absolute maximum. Maybe we're just looking for a local maximum. Right? Let's not worry about that distinction just yet. But how do I maximize this function? And I argue that if I, in fact, have a point that is in the interior, let's say, for example, like that one. Well, if I'm in the interior, I am free to move in whichever direction I might find useful for my own purposes, right? So we're in the middle. That means we can go in whatever direction, at least a little bit. If the function's differentiable, then derivatives mean something and I can draw conclusions from them. And if the gradient vector is non-zero, and I'm going to try to draw what I think the gradient would look like at this point. Looks like it's kind of increasing as I go into the page. If I go in the direction of that gradient, I know the function is increasing. So, well, if the function's increasing, then it again, not a maximizer, and we have eliminated that point as a possible maximum. Is that cool? I mean, you see that's the exact same argument, right? All right. Well, again, this applies at most points in the domain, unless one or the other of these conditions fails. And the failure of any of those conditions would mean that one of these happens. And again, we're going to call them critical points, even though what that means is we don't have any idea what's going on. All right, everybody happy? All right, now, as I'm sure you all recall, just because you have a critical point does not allow you to conclude that you have a maximum. So, for example, let's take this point right here. That point, assuming that the function is as I have it drawn, it does kind of appear to be sort of flat on the graph there. And so it looks like the gradient vector is 0. Does that mean that this is a maximum? Absolutely not. It's clearly not a maximum. Or does that mean that it's a minimum? Absolutely not. Clearly not a minimum. So, again, there's a lot of different possibilities. The geometry of 2 dimensions, here we have a 2-dimensional domain. Geometry of 2 dimensions is just more complicated than the geometry of 1 dimension, right? And so now we have to recognize that there is this possibility of this kind of weirdness happen where it's kind of concave up, if you will, in this direction, but it's kind of concave down, sort of in that direction. There isn't a single variable analog of this. That's a new kind of weird, right? We call them saddle points because this example here sort of looks like a saddle, right? Which, by the way, I think totally dates the terminology, right? Clearly, this terminology was invented before they invented Pringles, right? I think in modern times we would have to call this a Pringle point. Okay. So there are other kinds of saddle points though that don't actually look like saddles or Pringles, and it's a weird world out there, and there's lots of different kinds of saddle points. Oh, by the way, for a fun one, y'all can do an image search on monkey saddle. Give that a look, and there's a million others. Okay, so let's do an example. Let's find all the critical points of this function here. Notice that our domain is R2. Now again, we've got to go through all 3 conditions. We've got to check all 3 conditions. First condition, we have to look for points that are on the boundary R2 doesn't have a boundary. Every point in R2 is in the interior of R2. So we looked. There weren't any. Our responsibility is resolved. Next, we have to look at this function. Ask, where does this function fail to be differentiable? That's a polynomial. Polynomials are differentiable everywhere. Again, sweet. We did our duty. We didn't find any critical points based on either of these conditions. Quick word. These two conditions, I'm going to say in most cases you're probably going to encounter. Won't give any critical points, probably. That's not the point. We are not looking for answers. We're looking for reasoning, right? That's what we do in this class. And if you want to be able to argue that you have, in fact, found all the critical points so that your process of elimination argument will have legitimacy, right? In other words, if you want to be able to make valid claims eventually about the critical points that you do find, you have to have checked for all possible critical points. Right? So the observation I'll make, the analogy I'll make is, let's suppose you're trying to find who is the tallest person on Duke campus. I mean, if you don't check East Campus, you can't, well, I found the tallest person on West, and I'm going to declare that to be the tallest person on Duke campus. It doesn't work. That's nonsense. That make sense to everybody? You didn't check all the candidates. You don't have an argument. So with that in mind, you do absolutely have to check these two conditions. Whether the critical points you're looking for are found by those conditions is absolutely not the point. Here's the good news. It's usually really easy to check, right? Where's the boundary? Look at your domain. It's probably pretty straightforward, right? Where is the function not differentiable? And, glance. It's usually pretty straightforward. Okay, third condition. We compute the gradient. We set it equal to 0. We solve the resulting system. Not hard to persuade yourself y has to equal to 0. Likewise, x has to be plus or minus 1. And so, here's your two critical points. Everybody good? For the moment, we're not worrying about where to go from here. How do I classify these? That's another matter. We'll get to that in a couple minutes. Okay, now we got lucky on this one. This system of equations, this is a nonlinear, multivariable system of equations. They can be really hard to solve sometimes. In fact, arguably, they are usually really hard to solve. So here I crafted one that was very, very easy because I didn't want to get distracted by the algebra. But you should be prepared for the possibility that sometimes your algebra might be less friendly. Now, this system of equations does not come from an optimization problem, but something along these lines easily could. So let's just take this as a, for example, let's talk about how to solve this system of equations. And this one is actually also not so bad, but it does have a landmine in it, and so we need to talk about it. The first equation tells you x squared is equal to y squared. Lots of students will step on this landmine and conclude that x must equal to y. I mean, in my high school, certain classes, certain teachers that I had in my high school would have let that slide and consider, good enough. Let's not worry about it. But it's false. It's not true, right? You cannot just go around concluding x must equal to y. In this case, it doesn't have to equal to y. It could totally be negative y, and you have to consider both possible cases. Right. So let's see how those play out. Now again, two cases. X could equal to y. We'll do that one first. Then we're going to have to consider if x is negative y. totally separate situation. Easily done. Let's plug that into this equation. Let's see, that turns that into this, which is easy to solve. Everybody see how that goes? And by the way, of course, once you know y, these values of y, you plug into our case that we're, in fact, let me do it like this. You plug into our case that we're considering, and that gives us our actual critical points for those values of y. Okay, now, let's look at the other case. What if x is negative y? Well, that makes this algebra go down differently. That's not the same y equation that we had in the previous case. We get, as you'll notice, different values of y. And again, plugging back into our case, we get different, well, at least one different critical point. Right? If you've been sloppy with this algebra up here, if you ignored the possibility that x could be negative y, you would fail to get that critical point right there. Everybody happy? Everybody see the point there? Right? So again, obviously missing a critical point, unacceptable. Again, that you could then get a wrong answer to the question of where is this function as big as possible. And we can't take chances like that. Right? We have, our reasoning has to actually be valid. Okay. All right. Okay, so always be on the lookout for this case business. It comes up quite often, really, in this kind of algebra. Okay, second derivative test. Y'all remember in the single variable case, the second derivative test boils down to looking at the degree 2 term of the Taylor series. All right, you look at that, and roughly speaking, the argument is, well, if this is always positive, then you have a min. If it's always negative, then you have a max. And conveniently, a half is always positive, and a square is always positive. It's never negative anyway. And so whether this term is always positive or always negative just boils down to looking at the second derivative. Nice and easy. Just look at the second derivative. Plus means minimum. Minus means maximum. Easy. Well, this degree 2 term is more complicated. Right? Again, this is not just a product of 3 scalar factors and I can just make plus minus arguments. This is a sophisticated construction. And y'all probably remember this from linear algebra class. This is called a quadratic form. Does everybody remember quadratic forms? Long time ago, I'm sure. So we're going to approach this kind of the same way. There are 3 different possibilities. This quadratic form is either positive definite, in which case we have a minimum, or it's negative definite, in which case we have a maximum, or it's neither, in which case we have a saddle point of some description. I don't know who knows what kind of saddle point. Okay. Now, how do we decide this? Well, there's a whole story there that I'm sure y'all probably have vague memories of from your algebra class. In this case, it breaks down in a nice way. We can make various cool arguments, and this is optional. You don't have to worry about this. If we were to go through and discuss this carefully, this would be a good solid half-hour discussion in some of the harder ideas of linear algebra, and it's a beautiful argument, and I like it a lot, but I can't justify spending class time on it, so you don't have to worry about this. If you are looking for a challenge, and if you're interested, what I've done here in this second line is I've left a little trail of breadcrumbs. Try to, there's a lot I've left out on purpose, right? But try to fill in the blanks there, and then you can draw the conclusion that we're about to write down, which is what you do need to know, and that is the second derivative test. By the way, this is only for 2 dimensions. And here's how it works. We have to first look at the determinant of the Hessian matrix, as it turns out. Positive would mean that we get a, let me do it like different color. Positive would mean that we get a fairly familiar sort of reminiscent of single variable. Positive means minimum, negative means maximum. All right, so you look specifically, you look at the unmixed second partial. Either one of them works, by the way. If you want to use FYY for whatever reason, you may. Anyway, I wrote FXX because why not? But if FXX is positive, you have a min. If it's negative, you have a max. Nice, simple story if that determinant is positive. If it's negative, you have a saddle. What kind of saddle? Oh my gosh, no idea. Who knows? Could be lots of different options. But negative means saddle. And then lastly, it is possible that determinant will equal to 0, in which case the test fails, which I cannot emphasize enough. It doesn't mean that it's not a maximum. It doesn't mean it's not a minimum. It doesn't mean it's not a saddle point. It means we just don't know. Right? This is a, back to the drawing board. We're going to have to try something else. All right. How are we doing so far? Okay. Let's do a plug and chug example. We've already looked at this function. We've already found its 2 critical points. Let's do some preliminary work. Here's the Hessian for that function. Again, matrix of second partials. Make sure you can do that, of course. Here's the determinant of that Hessian. Super easy little calculation. And now let's play the game. Let's start with this point right here, -1, 0. Well, that point, plug it in to see what, oh, I'm sorry, I got that wrong. That point, plug it into the sorry, I did have it right. That point, we plug into the Hessian determinant. It is negative. That means we have a saddle point. Everybody happy? It's plug and chug. Right? Just follow the rules. Looking now at this other point, 1, 0, we take that. I keep hitting the wrong. We plug that in to the Hessian determinant. We get positive, which puts us up here, which means that I now have to look at fxx, which, again, you can just plug in this point into fxx, positive. And positive means local min. Everybody happy? See, that's very plug and chug. All right. Okay. All right, real quick on this next business. This isn't really, arguably we don't have to do this, but I think this is important, so I want to say a quick word. Not all maximization questions actually have answers. If you're looking for the absolute maximizer of a function, it might not exist. Right? And here's a couple of scenarios. If this is my domain right here, right? And here's the graph of my function. There is no maximizer, right? There is no absolute maximum value. The function just keeps getting bigger and bigger and bigger endlessly as you approach the open-ended left sort of endpoint. So there is no maximizer. So if you find the critical points and look at the values at those critical points, and then find the one that's the biggest and say, well, that's the biggest value of the function among all my critical points. And if you declare this to be the absolute maximum value of the function, well, that's garbage. Right? Does everybody see that? So there's a hidden assumption, what they show you in high school, and depending on how careful the treatment is in a high school calculus class, sometimes they'll just say, well, look for the critical points, see where it's the biggest, whichever one's the biggest, that's, okay, game over, victory. Right? It doesn't work. So, whoopsie. Right? We've got to be careful about this. So, there are other ways that this argument can fail. You might have a domain that has no upper bound. You might have a discontinuity, which, by the way, you would have to declare this as a critical point because it's not differentiable there, but the value of the function does exist, and it is not the maximizer, right? So, again, in some sense, there are three different ways that the old casual take on optimization can fail. And good news is these are the only three ways that it can fail. So, if your domain is closed, in other words, none of that nonsense. And if your domain is bounded, in other words, none of that nonsense. And if your function is continuous, in other words, none of this funny business. If these three conditions are satisfied, there is a maximizer that does achieve the absolute maximum value of the function on that domain. So you got to check these three conditions if you want to actually find an absolute max. Okay. All right. Now the next page and a half. Look at all this algebra. Look at all the square roots and pluses and minuses, and oh my gosh, this is a tedious bit here. We're going to skip this. You can look at it if you'd like, but you don't have to. The reason we're going to skip it is because there is a much better method for how to treat stuff like this. I'm going to show you the better method. I strongly advise that you should use the better method, right? And I only leave this in the notes for the spectacle of it all. Of, oh my gosh, look at all this stuff that thankfully we don't have to mess with. Okay. All right, so here's the better method. So this is called the method of Lagrange multipliers. It's an optimization thing. There's some function we want to optimize. Want to make this some function as big as possible. But with a constraint. So you can't just pick whatever value you want. There's some other equation that has to also be satisfied while you're optimizing. So here is an example. Suppose I want to minimize distance to the origin. Right? Closest to the origin means I want to minimize distance to the origin. How do I minimize distance? Well, how about 0? I don't think you can find a distance less than 0. Right? I'm going to propose that 0 is the minimum value of distance. Unacceptable. Because a distance from the origin of 0 would mean that I'm looking at the origin itself, and the origin doesn't satisfy the constraint. Right? So the constraint is what makes the question interesting. I don't want to find the point closest to the origin. That's obviously the origin. I want to find the point on this curve. Just among points on this curve. The one that's closest to the origin. And this is a much harder problem. Everybody see what I'm describing there? So a little bit of lingo. There's always going to be some function that you want to optimize. We're going to call that the objective. And there's going to be some function that describes your constraint. We're going to call that the constraint function. And specifically, the constraint function is the function for which a level set gives the constraint. It's very important that we phrase this as level sets. If you look in this original example, this constraint is phrased as a level set of a function, that is our constraint function. But this equation, sometimes your constraint will come to you not written as a level set. Rewrite it as a level set. Right? Move the algebra around so you have stuff equals constant. We're going to need it to be a level set. Okay, couple of quick examples of why we would be interested in this. When do we need to deal with a constrained optimization? Well, if you want to make the volume of a box as big as possible, volume is your objective. But I need a given amount of area. Area then is my constraint. And when I say given amount of area, I mean I'm looking at a fixed value of that area function, and namely I'm looking at area equals a constant, namely I'm looking at a level set of area. That make sense? All right. And there's another example there y'all can take a look at. We're just short on time, and anyway. Here's the argument. It's another one of these elimination arguments. Suppose we have a constraint written as a level set of some constraint function g. If these three conditions are satisfied, I claim that the function is increasing, and therefore this is not the maximizer that we're looking for. Okay, so how do I know that this, how do I fill in the blanks on this? Well, if the functions f and g are differentiable, that means the gradients tell us useful information. If gradient of f is not a multiple of the gradient of g, wait a second, what's the deal with the gradient of g? The gradient of g is always perpendicular to the surface because it's a level set. If the gradient of f is not a multiple of it, then that means that the gradient of f is pointing off of that perpendicular axis, which means that its projection, like so, points in a non-zero direction, and that's a direction that I can go along the surface, right? I can just start going that way, and I'm going to have to curve along with the surface as the surface curves, but that represents a direction that I can go. And how fast is the function changing as I go in that direction? Well, as I go in that direction, gradient dot v, that's clearly an acute angle. That means this is going to be a positive directional derivative. The function's still increasing. And therefore not a maximum. Everybody good? Okay. All right, so again, the way we turn this into a useful process is we look for where one of those conditions might fail. We've got three conditions to fail. Again, we call these critical points. This one I like to call the differentiability condition. For reasons that I can't talk about in this course, this is called the degeneracy condition. Really good reasons for this. It's not something we can go into. And this is the method of Lagrange multipliers, and the lambda, by the way, is what we call the multiplier. It just means a scalar factor. And so this we'll call the Lagrange condition. So we just have to check those conditions. It's just like in single variable. It's just that those conditions now look a little bit different. So let's go through an example. I am going to point out the first two, again, usually pretty easy to check. Here we have a couple of polynomials. They're obviously differentiable. Write that down. Right? That shows that you know that you're supposed to check that. It's super easy to check that. Now you just impress the grader. You probably got a point out of the deal, right? Don't leave the money on the table. Get those points. They're easy points. Okay. Where's the gradient of g equal to 0? Well, it's a little bit of linear algebra there. Pretty easy argument. You do have to compute the determinant of that matrix to argue that this only happens at the origin. And then, of course, at the origin, constraint's not satisfied, so it's not our problem in the first place. I don't need to eliminate that point. Okay, make sure to write those down. Again, that's points. Don't lose points. Lastly, here's our Lagrange condition. Keep in mind, we're trying to eliminate points from the constraint set. which means we're only interested in points on the constraint set, which means the constraint, of course, must also be satisfied. So altogether, in fact, what we have is a little system of 4 equations. Systems of 4 equations. Again, the algebra can get a little weird, so let's focus on the algebra. In this case, the first thing we need to do is, rephrase. What I would like to do is take these 2 equations, cancel the lambdas, right? So that I can then rewrite and solve and find a relationship between x, y, and z. That's what I would like to do. Here's the problem. I can't do that. I can't cancel something until I know it's not 0. Can't cancel. Is everybody super clear on this, by the way? You can't cancel zeros? Is everybody 100% clear? Okay. Because keep in mind, canceling is dividing. You can't divide by 0. So I need to first establish that it's actually okay to cancel the lambdas, and here's the thing. That right there tells me that lambda is definitely not 0. And if lambda is not 0, then it is in fact perfectly fine to cancel the lambdas. Everybody good? Okay. All right. So it's all over but the shouting at this point. Once you have a relationship between x, y, and z, you can rewrite the constraint in terms of a single variable, solve to get that variable, plug that back into this relationship, and that'll give you your critical points. Pretty straightforward strategy, really. Everybody happy? Okay. Here's the next little algebraic bump in the road you might encounter. Again, let's not worry about the first 2 conditions. You got to make sure to do those, get those points. Don't leave money on the table, but doesn't require discussion. How though do we solve this system? And here's what I would like to do. I would like to do what's called eliminate lambda. Eliminating lambda means solve for lambda in both of the equations. If you have 2 formulas for lambda, those formulas must equal to each other. Very clever little argument. Ultimately not a deep point, but it's very handy. This is one of the more common, useful foot in the door for this kind of algebra. Solve for lambda in both equations, set those results equal to each other. And then, of course, you notice that means that x has to equal to negative y. And once we have that, we can put that into the constraint. The constraint turns into that, which is easy to solve, yada, yada, yada. Okay, but wait a second. Can I do this? Can I solve for lambda? Well, I would need to divide by x, and I would need to divide by y. How do I know they aren't 0? Again, you can't divide by 0. It's a big deal. So before any of this, you have to establish that x and y are not 0. This is actually pretty easy to do. Just take 0 and plug it into these equations and notice that they fail. Right? So again, it's easy to actually to establish that what you would like to do is perfectly valid, but you do have to establish that. Everybody good? Okay, last example. And this has a really tricky point in it. So again, question, objective function, constraint function, check for differentiability, check for degeneracy, blah, blah, blah. Let's get down to the good part. Here's our system of equations. Again, that's our Lagrange condition and our constraint together. Okay. Let me show you the wrong way to do this first. Dramatically wrong, hilariously wrong. A lot of people would say, well, check it out, lambda clearly has to equal to 1. Oh, but wait a minute, lambda also clearly has to equal to a 4th. That's a contradiction, no solutions. Everybody see the lure? It's tempting, right? You're going to want to step there. Don't step there. The only way you can argue that lambda would have to be 1 is if you know x is not 0 because you're canceling the x. You can't cancel things until you know they're not 0. Okay, so nasty little business. So the way we proceed on this is we first acknowledge that the origin does not work. You can plug in 0, 0, 0. It clearly fails. That means x and y and z can't all be 0. Okay, if they can't all be 0, then at least one of them has to be non-zero. And what we've done now is we've identified how to break this down into 3 possible cases. So you have to check each one of these 3 cases separately. Let me show you how these break down. Let's look at this first case. If x is non-zero, well, then lambda truly is 1. If lambda is 1, then y and z have to be 0. And if y and z are 0, then x has to be plus or minus 6. Right, so it's a multi-step process. You've got to be careful and think it through. But that allows us to conclude 2 critical points, right? Each one of these is a critical point. So we just found 2 critical points. And I'm going to let you all fill in the blanks on these other 2 cases. That gives us each 2 more. So grand total, there are 6 critical points. And let's just take a moment to recognize if you were a little too sloppy, if you're a little, who cares about this 0 nonsense, that's just stuffy mathematicians, right? Then you'll find 0 critical points when in fact there are 6. So pretty dramatic problem. Okay, we're done. Enjoyed teaching y'all this semester. Look forward to seeing y'all on Friday. Good luck studying and all that. Oh, I hope everybody got the email about pencils. Now good. Just make sure they're decent pencils and they make a nice dark line. All good. See y'all later.
Why would you post that?